So I'd like to thank you, Paul, and the organizer for the invitation. My name is Gustavo Lima. I'm Brazilian, but I work at Chile. So this is why I have these nice pictures here to motivate you to come and visit us. Okay, so today I will talk a little bit about the recent research we are doing there about using multicore fibers for high-dimension quantum information processing. How can I change the slides? I don't have the, sorry. Okay, okay. Here's the outlook of my presentation. So we know that multiport beam splitters are crucial for high-dimensional quantum information processing. And for me, the easiest way to show this is to show that in the experiments, we need them to be able to assess the many outcomes of simple projective measurements you can do. So, but the problem is that the fabrication of this device has been proven to be difficult with only recent progress with integrated photonics technology. And actually, most of the high-dimension quantum experiments done to date, they are based on inefficient post-selection detection schemes. So this is more or less the line of thinking that I use to present the multiport beam splitters we have been able to fabricate with the multicore fibers. And then I will show how this device they can be used for building programmable quantum circuits and how we use them for doing a work in collaboration with Paul for the generation of random numbers. Okay, so there are many different strategies for encoding qubit states, and one of them is based on the transverse moment of single photons. There are two approaches in this case. One based on the linear transverse moment of single photons, where you define path qubits, and the other based on the orbital angular moment of qubits, and where you use to generate the qubits, you use the manipulation of Laguerre-Gaussian modes. So I would say that the most typical technology for generating these qubits is the spatial light modulator in here. This is a very practical tool because you can control the amplitude and the relative phase of the transmitted light. So you have good control of the qubit states you generate. You can control the amplitude and the phase of the states, the imaginary and real parts of the states. But the spatial light modulators also are the most used tool for detecting these states. And here there is a problem. Okay, so how does it work? You have the spatial light modulators. You use an inverted phase pattern for post-selecting the state you want to detect. And okay, so the system is based only on using one single detector. It's also very inefficient. For example, you can see here that even when the generated state and the state selected for detection is the same, the efficiency of the process is very low. We can talk about this later. And so what I want to show is the problem of having only a single detector. And to see this, for example, we can have a look on high-dimension quantum key distribution. This is the key rate generated in the BB84 protocol. So, okay, if you have one detector scheme, what you have is a detection efficiency that decreases linearly with the dimension of your system. And if you are using a high-dimension quantum system, the amount of information you put there increases only logarithmically with the dimension. So at a certain point, you start to lose more than you get. And for example, in the case of the BB84 protocol, you can see that already in here, with dimension 8, you generate less key than you can generate with a four-dimensional quantum system. So there is no reason at all only using this scheme for high-dimension quantum information processing. So this is not the case when you have access to many outcomes of the measurement. And so to move in this direction, we left the technology of spatial light modulators and start to work with multicore fibers. Okay, what are them? Okay, so in classical telecommunication, you have this multiplexing thing, which is a technique where you want to increase the amount of information you transmit over the fiber, and to do this, you use different physical properties of the light, like polarization and frequency, for instance. And it's interesting to see this graph here because we have been able to maintain this trend over the last 40 years. Every 4 years, the amount of information we propagate over the fiber increased 10 times. This is something you have seen in your life. For example, probably today, you pay the same that you paid 10 years ago in the internet, and it's much faster. So, but there is a problem with this, which is that we are achieving a fundamental limit on the amount of information we can transmit over one fiber. This is a consequence of the quality of the glass we are using and scattering effects. So the new idea is to use the spatial division multiplexing technique, and it's based on new designs of optical fibers. One of them is this multicore fiber. What is this? You have a fiber, conventional fiber, where inside the same cladding you have multiple cores. And this technology is amazing. It has been used to show that you can download 1 terabyte of data in 0.03 seconds. And so we decided to try it for quantum information processing. And we showed that, okay, the idea is to encode the qubit states on the core modes available for the photon transmission inside the fiber. There are fiber up to 19 cores built already, so you can increase larger dimensional quantum systems with them. And the idea is that since you have the cores inside the same cladding, the fiber is intrinsically stable against thermal and mechanical fluctuations, no? So we have used these fibers, and we did this experiment here to implementing a high dimensional quantum key distribution over 300 meters of these multicore fibers. But in this experiment here, we were still working with a single photon, with only a single detector. And then we started to do research to solve this problem. And okay, so the first thing we need is to be able to access all the cores of the fiber individually, such that we can set relative phase between them, and we can put the detectors over there, right? And this is also this is also a problem for classical telecommunications, because if you want to use the fibers for class communication, you need to build the repeaters, and so you need this device. And so we start to look at the works that were done in this direction at classical telecommunication, and we found many researches and many works. I like this one because it's recent and it shows how complicated it's. Very elaborated, even though it's not practical at all. But at the end, we found this working here, which is quite interesting. I can't get too much in details, but the idea is to get conventional single-mode fibers. You put them together, you polish them until you get the separation between them, matching the separation of the cores inside the multicore fiber. And then you glue everything together with the multicore fiber, and then you build this demultiplexer device in here, so you can map the signal in one core to an independent single-mode fiber. So we start to discuss this idea with our US company, and they decide to try it. So here you can see the device. We have the 4 fibers here, 4 single-mode fibers in here. They are glued together here with the multicore fiber. It's coming out here, so we have the multicore fiber with 4 cores in here. And we have also this device for the 7-core configuration. So, okay, this was the first device we had to develop. And then the second one is the device that allows us to combine the cores together, no? Which is the multiport beam splitter. So, again, I start to look what people were doing in this direction in classical optics. And surprisingly, I found many interesting things. For example, people were considering using the multicore fibers to build the multi-arm interferometers for optical sensors for doing multi-parameter estimation. So there are many different strategies I found. We tried some of them. For example, in this case here, you throw light into the cladding of the multicore fiber, and through evanescence field, the light couples to the cores. Okay, this is not good for quantum information because the losses are prohibitive. But then I found this paper here, which is quite interesting. because the authors, they were using this new different type of multicore fiber, which they have trench on them to protect the light to couple from one core to another. Okay, these fibers, they have this type of refractive index profile, and they are interesting. It was interesting to them because of this structure, each core has two modes of two modes of light propagating over it. One inside the core, which is a Gaussian mode, and another one outside the core, which resembles a Laguerre-Gauss mode. No, they are orthogonal. They do not interfere, but they use a new technique for tapering the fibers. They use an arc discharge of the fiber to heat it homogeneously and start to pull it in opposite direction. So the core starts to get smaller and smaller and smaller, and then these modes start to overlap and they got interference. So they could use each core for doing multi-parameter estimation, and one for measuring the temperature, the other for measuring the strength of the sample. So it's a nice idea. And then we thought, well, maybe we can just get conventional multicore fibers, use the same tapering technique, and it may be enough for building a multiport beam splitter. Why? Because during the tapering process, the cores will get close together, and if you can do it, throwing light simultaneously through the fiber, you can control it. So we discussed this possibility with the fiber core company. They decided to try it. It worked. And so here you can see the multiport beam splitter fabricated in the lab. Here are some results of it. You can see that the outcome is really good. The insertion losses are very small, 3% only, and the split ratio is almost perfect. And you can do it with 7 cores, 19 cores, so it's an interesting thing. Okay, and so we had all the devices that we were looking for, and then we realized, okay, maybe we can do more with this. And then we realized that we could do a programmable quantum circuit, based on telecom technology. So here is more or less the scheme of it. And you can throw light on it using any quantum light source. And then you use a demultiplexer to put the light into the multicore fiber beam splitter. And then you have a multi-arm interferometer, which is the programmable circuit you have. You can have here phase modulators, fiber built-in phase modulators for example, generating the states you want. And you can also, you can build the main outcome measurement like we were discussing, combine this device. And also you can have another set of phase modulators in here to change the settings you are using, you are detecting the states. And why is this interesting? First, because since you are using off-the-shelf technology of telecom, this can work at up to 10 gigahertz of repetition rate. And also because even though we get to single mode fibers in here, the core, the diameter of the cores involved are always the same. And so the overlapping of the modes into the beam split should be very high. So, okay, we did a prototype of it. Here is a photo of it. So we had the system working at 2 megahertz, which is fast for comparing with the actual high dimension quantum experiments. We did a very simple closed loop circuit to stabilize it. It's a very simple thing to be done, and the system can work for hours and days. So we test the optical quality of it. You can see it's very high. We could get average visibility of 99%, higher than 99%. And this is quite important because we are here proposing many new technologies. And today, with the new protocol, with the new approach of device-independent quantum information processing, it's not enough anymore to violate bare inequality. You need this high visibility, no? So, okay, everything was looking fine, so we decided to use it for high-dimension quantum information processing. So we did a work in collaboration with Ivan, Paul, and Danielle. And the idea was to use our system for generating random bits in this measurement device-independent scenario that I will explain next. And why is interesting? This is interesting just because since we have access to all the outcomes of the measurement, in principle, we can generate 2 random bits per round of the experiment, which is the double of what you can do with qubits, no? And so, okay, what is the idea of measuring device-independent quantum random number generators? You trust in the source. It's very similar with what we do in quantum gate distribution. And you have a measuring device that is supposed to do something. For example, here to measure in this base, and if you detect this state, you're supposed to have a clicking detector, and that's it. But the so how can you use it to generate random bits? You just need to send a state here which has a no-null overlap with the measurement base states in here. So the clicking detector will be random. But the problem is that we don't trust the device. And also, there could be some type of detector side channel attack going on here. So how can we make the random bits that are being generated private? So Paul and Daniel, they had a very interesting idea, very simple. And the idea is to add here in the protocol a second event where you send one of the base states for detection, so you know which is the detector that should be firing, right? And you are still sending the mutually unbiased state, and 90% of the time, so you are generating random bits. But with this event here, you can set a bound on the guessing probability of the random bits generated at event 1. And then, if you have higher, you can show how much is the private randomness generated, and you can see that if you can get higher visibility, the amount of private randomness will be high, okay? So we use the system to implement it. This is some of the results we had. Typically, we could have, we had 50,000 kilocount recorded per second. We were able to maintain a mean average visibility higher than 99.4% all the time. And here are some of the results. This is the amount of private randomness generated. It's around 1.2 bits per experimental round. So so our system was capable of generating 60,000 private random bits per second. And this result I like very much because it's kind of interesting because it shows the relevance of using high-dimensional quantum system. We were able to beat the 1-bit limit. So, okay, this is more or less what I had to show. So, some concluding remarks, no? I think it's interesting to have this telecom-based approach for building programmable circuits because it's totally compatible with what people are doing with integrated photonics. So, let's say you want to communicate two circuits, and you can have something like you can connect them with multicore fibers, and maybe on the fly you can do some information processing that you may need. And also it's interesting because it can be used independently for quantum information processing, and it's easy to adopt this system at other platforms for quantum information process like optical trapping and optical tweezer. So that's it. Thank you for your attention.
Very much, Gustavo. So we have time for questions. I think there's Will.
Gustavo, so it looks like in the readout stage you have 4 phases you can control. And
yes, actually we just need 3 because one path is 0. It's just relative phase. No? Okay, so but yes, we have 4 phases.
For general rotations of a 4-dimensional system, you might need many more phases. Have
no, actually,
cascading these?
So, no, please finish and then.
Have you thought about cascading many together so you
exactly.
have more phases?
Yes, you need to put them together to be able to implement more general operations, like it's done with the multiport device when you have mesh of beam splitters.
Hi. How to stabilize the path lengths or match the path lengths?
This is very simple. No? For example, we have integration time here in our case of 0.1 seconds. Okay, so you can check the. Let me put in here. So you can check the counts you have during a time interval, let's say 0.1 seconds. You see that you can set a threshold looking for the counts on the other detectors, no? And for example, you can put a threshold of 99.5%, and the system keep playing with the phase until you get to this point, and then you start the procedure. You can do it in 0.1 seconds, because in 0.1 seconds we have like 10,000 counts.
Okay, cool. So about the path length. So when you
Sorry?
say like, if you splice this device together, how do you make sure that the fibers?
No,
are
these
all the
devices
same
are
length?
not spliced together. Each
Oh,
one
okay.
is composed of fibers. You mean, what do you mean?
So like the
Huh?
How do you match the lengths of
Yeah.
With the phase modulator. The phase modulator is doing this. It's
So
playing with the optical path of the interferometer.
the gap between the couplers on each path is exactly the same, like to within
No,
a
no,
coherence
you
length?
have fluctuations in phase which are a consequence of the path of each arm varying in time. So you can fix it with phase modulators. This is what they do. They play with the optical path of each arm. You see?
Yeah, I guess in my head, I struggle to see how this device is made where
No, you play
the
with
paths
the...
have the same length before, like when it's off.
No,
The
for
paths are
example,
within a wavelength of each other.
just to give you an idea, you can play with the refractive index of this device in here, right? Let's say you have, you play with the refractive index of it, so you can make it larger or longer, effectively larger or longer, larger or shorter, sorry, by playing with the refractive index of the fiber here, right? So this is what you do to control the phase of the fluctuations of the interferometer.
Okay, thanks.
So if there are no other questions, then let's thank Gustavo once again.
Thank you.